We've talked about the properties of waves, including some properties that are unique to waves. Chief amongst those, the ability to be in more than one state at once. You can have one oscillation of a medium and another oscillation of a medium, and they can both be there at the same time, and they just add constructively or destructively to any point in the medium. Also, waves within a medium, their speed is only really affected by the medium. If you have a particular shape of wave in a particular medium, it must do something. It can't be faster or slower than that because the only reason it's moving is because of the interactions of the different parts of the medium with each other. What we haven't talked about is what happens when a wave is moving in a medium and the medium changes, either fast or slow. What happens at the boundaries of media? So if you take a still pool of water in a bathtub or something with a clearly defined boundary, and you start making a disturbance in the center, then it's going to send out ripples. And the ripples will go out, and you'll see this happen. And they'll get smaller as they go out because the energy has to be spread out across the entire circle. So the amplitude goes down, but it's still heading out. And what happens when it hits the edge? Well, you've seen this, and if you haven't seen this, you can go and see this any time. What happens is that those ripples reflect. And so the wave reflects, and it bounces off, basically as a lovely mirror image, just like normal optical reflection, and comes back. And so these waves will be going out, or in this direction they'll be going forwards, and these waves are coming back and spreading out. And what you get is these beautiful interference patterns as the ripples go on top of each other. Now if you watch that really carefully, which is probably easier with just a one-dimensional wave, like a string up against a wall or something heavy, so you have a string attached to a wall and you're sending a wave at it, then what you'll find is the wave reflects fine, and in fact goes upside down when it does the reflection. So it'll come up to this wall and reflect and come back pretty much exactly as it came, except upside down. And if you have a less dramatic kind of transition, for example, you might be going from a light rope to a heavy rope, then what's going to happen then? Well, if you put in a wave, then when it gets to that boundary, something interesting will happen. And the first thing is you get a reflection. So that wave is going to reflect just as though it had bounced off something hard. But the extra interesting thing that will happen is that you'll also have some of the wave continuing to go on the way it was before. And so in this large, heavy piece of material, you'll actually get a small wave going forwards as well. And so what you get is you get reflection, yes, but you also get transmission. And this is something, of course, that a wave can do that a particle can't. You can have it go through and come back at the same time. Now, of course, the energy in this part of the wave plus the energy in this part of the wave can't be greater than the initial energy, but you can still have both transmission and reflection provided you get the right amounts of each. Now, if you go the other way from a wave in a heavier material like this that transfers into a light material, then you'll get transmission and reflection again, but the only difference is that in this case, the reflection doesn't go upside down. And the property that affects whether or not a wave is going to reflect at a boundary doesn't depend on any other property of the material really, other than the speed of the wave and the way the speed of the wave will change. So in this region, the speed of the wave is fast, and when it goes into a slow speed area, it tends to reflect and invert. And here we're going from a slow speed to a high speed area. We've already seen what happens when we have a pulse going one way get superimposed with a pulse going the other way. But let's see what happens when we have a continuous wave going to the right interacting with a continuous wave going to the left. So here we have a wave going to the right. It's just a sinusoid and it's traveling along, and it has a certain speed, which is the frequency times the wavelength. And if the frequency is higher, then if we sit at one point, then things go faster, and that means that because the wavelength hasn't changed, it means the whole thing is traveling quicker. Equivalently, if we make the wavelength bigger, then we can see it's getting longer on this axis, and indeed the actual peaks are moving faster again. If I want to change the direction of the motion of travel of that wave, all I have to do is put in one minus sign into my equation, and there it goes, going backwards. Now the question is, what happens if I have one of these going to the left with a particular frequency, plus one of those going to the right with exactly the same frequency? So the best way to visualize two sine waves passing through each other is to see two pulses going through each other and then make the pulses wider and wider until they just cover all space. So there's two pulses, they pass straight through. Let's start that again, except this time we'll make them wider. And you can see when they pass through, you get that sort of pulsing interference pattern for longer. And in the limit where they're infinitely wide, so we make them super, super, super wide, then you just get pulsing and nothing else. And if we slow that down, I'll just slow that down, you can see that what you're getting there is an interference pattern that's going up and down. If you sit at any point, you can see that those peaks are not traveling left or right, they're standing still. And this is called a standing wave. And these points here, where the standing wave is moving a lot, are called antinodes. And these points here, where it's not moving at all, are called nodes. So here's our standing wave, where both the frequencies are the same. Now what happens when we make the frequency of the wave moving to the right a little bit higher than the frequency of the wave moving to the left? Let's do that. And what we see is we still kind of have a standing wave, except now we can see that it's moving. And so the nodes are moving and the antinodes are moving. So it's still oscillating, but now the nodes are moving. And if we change the frequencies so that the frequency of the wave to the left is a higher frequency, we can see that the antinodes and the nodes are all moving to the left. So if you want a proper standing wave, you've got to organize for the frequency for a wave going one way to be exactly equal to the frequency for the wave coming the other way. And the best way to organize that is to have it reflect off something. For example, you might have a string, and if the string has a fixed point at one end and a fixed point at the other end, then if I induce some kind of wave here, it's going to travel along and bounce and come back. And so the frequency going in each direction is going to be the same, and what that means is I'm going to end up with a standing wave, naturally here. Now if I pluck a guitar string, I'm going to get a very specific kind of standing wave, a particular one. And the reason for that is I have to have a standing wave that has to have a node at the end. At each end, in fact. And there are only certain wavelengths of wave that can have a node at each end.